Hello, sixth grade scientist. This week, we're going to be focusing on magnetism and energy and electricity. So, we're going to be starting on page 4 of your fill-in-the-blank booklet. There's page 4. It has a picture of a battery and a nail and wire at the bottom. And then you see this this magnetic field underneath the picture of the car. So, let's get started. You should be focusing right here in the fill-in-the-blank book. Let's get going. Magnetism is the force of attraction or repulsion of magnetic materials. A lot of what we're going to go over, we've already seen that you have done this in the 4th grade in your magnet unit and in your electricity unit. So a lot of this will come very easily to you. So, magnetism is the force of attraction or repulsion of magnetic materials. Surrounding a magnet is a magnetic field that applies a force, a push, or a pull without actually ever touching an object. An electric current flows through a wire and it's wrapped around an iron core, and that forms a magnet. A coil of wire wrapped around a magnet, or a magnet spinning around a coil of wire, can form an electric current. I had to write the word in for wrapped because I accidentally erased it. Sorry. Anyway, an electric current flowing through a wire wrapped around an iron core forms a magnet. But a coil of wire wrapped around a magnet, or a magnet spinning around a coil of wire, can form an electric current. Make sure you get those down. Examples of how magnetism and electricity are interrelated can be demonstrated by the following devices. An electromagnet. This is a picture of an electromagnet. An electromagnet is formed when a wire in an electric circuit is wrapped around an iron core, producing a magnetic field. So an electromagnet is formed when a wire in an electric circuit is wrapped around an iron core, producing a magnetic field. The magnet that results loses its magnetism if the electric current stops flowing. So let's look at this example right here. Here is a battery. What kind of energy is inside a battery? That's right, chemical energy. Chemical energy inside the battery is sent out into the wire. What kind of wire? Copper wire. Copper is the best conductor of electricity. So copper wire is the type of wire you are going to be using. Copper wire is then wrapped around an iron core. In this instance, it's a nail. The more times that I wrap the wire around, the stronger this electromagnet is going to get. The bigger the battery that I connect to the electromagnet, the stronger the electromagnet is going to get. So you can make it stronger 2 ways. Either continue to wind more and more copper wire around the nail, or get a bigger battery. The second that this copper wire ever comes disconnected, immediately the current would stop flowing and it would lose its magnetism. And that's an electromagnet. A generator, on the other hand, produces an electric current when a coil of wire is wrapped around an iron core and that's rotated near a magnet. Generators at power plants produce electrical energy for our homes. So here's a generator, and it is a coil of wire wrapped around an iron core. So there's a coil of wire inside here, and it's wrapped around an iron core, and then that's rotated near a magnet, and that magnet allows it to generate electricity. So we have a song for that. I will sing it with you in just a second. It's a chant. and it produces electric energy for our home. A generator contains coils of wire that are stationary. That means they're held still. And rotating magnets that are rotated by turbines. Here's the turbine going round and round. Turbines are huge wheels that rotate when they're pushed by water, wind, or steam. So either water is going to make the turbine go around, or wind is going to make the turbine go around like a windmill, or steam will make the turbine go around. Thus, mechanical energy is changed to electrical energy by a generator. Smaller generators may be powered by gasoline. Here are a couple other pictures of generators. So, the core, the wire. You can see the electricity is traveling through. And then over here, which is more of the one that you'll actually see in lab, the magnets are on the outside, the coil of wire wrapped around the iron core is in the inside. So what's the chant for generators? Here's how it goes. It's called Generators Generate Electricity Chant. And this is how it goes. Generators generate electricity. For who? For me, me. Mechanical to electrical, mechanical to electrical, mechanical to electrical, me. Generators generate electricity. For who? For me, me. Mechanical to electrical, mechanical to electrical, mechanical to electrical, me. Again, generators generate electricity. For who? For me. Mechanical to electrical, mechanical to electrical, mechanical to electrical, me. Now, why do we sing that? Because generators generate electricity. For who? For me. What does the me stand for? Mechanical energy transformed to electrical energy. Mechanical to electrical, mechanical to electrical, mechanical to electrical, me. Every single year for the past several years, we have had students that could not remember that generators generate electricity and that they do it from taking mechanical energy and changing it into electrical energy. So, we are doing this energy transformation from mechanical to electrical in the song. One more time. Generators generate electricity. For who? For me. Mechanical to electrical, mechanical to electrical, mechanical to electrical, me. Now you sing it along. Everybody, nobody sit there not singing. Teachers double check them. A 1, a 2, a 1, 2, 3. Well, generators generate electricity. For who? For me. Mechanical to electrical, mechanical to electrical, mechanical to electrical, me. Now, that's not the only chant we have. Generators are generating electricity, changing mechanical energy to electrical energy. But we have something that's doing just the opposite. And we have to memorize a chant for that. So what's making it go the opposite way? It's called an electric motor. An electric motor changes electrical energy to mechanical energy. So this is its opposite. So a generator was creating electricity and making it go from mechanical to electrical. But an electric motor does just the opposite. It goes from electrical to mechanical. So, look at the word electric. It starts with an E. Look at the word motor. The motor starts with an M. Here's E to the M. E to the M. Electrical to mechanical. E to the M. And so we have our next chant. But let's finish these notes before we sing that chant. So, an electric motor changes electrical energy to mechanical energy. It contains an electromagnet that rotates between the poles of a magnet. The coil of the electromagnet is connected to a battery or to another source of electric current. When an electric current flows through the wire in the electromagnet, a magnetic field is produced in the coil. So this electric motor has to be connected to a battery. We're connecting it to an electrical source. So when you have an electric motor and you turn it on, it already has electricity. It has electricity either by a battery or by hooking up to the electric company. So you're not making electricity with this. You're converting it into mechanical energy. So you're using electrical energy that you already have and you're turning it into mechanical energy. So it's an energy transformation that's just the opposite. But remember, in the generator was generating electricity. So we were creating electricity from transformation. So with the electric motor, you are using a battery as your source of electrical energy to make mechanical energy. So what is that song? Let me see. Right before we are ready to sing the chant, we've got to finish the next part. Like poles of the magnets inside the electric motor repel, and unlike poles of the magnets attract. This causes the coil to rotate and rotate and rotate, and then it changes electrical energy to mechanical energy. This rotating coil of wire can be attached to a shaft and a blade in an electric fan. So you've always wondered, how does a fan work? Mrs. Massey has a couple on her desk. I know that the other teachers have fans, or at least a fan inside their computer. How does that fan work? Well, it's an electric motor. It's transferring electrical energy into mechanical energy. So it's electrical to mechanical. Electrical energy can be transformed to light, sound, heat, and mechanical motion in an electric circuit. An electric circuit contains a source of electrical energy. A conductor of the electrical energy is the wire. And I'm going to tell you right now, write the word really big, copper. Copper is your friend. Copper wire is your friend. It is how all of the good connections happen. Whenever you're doing anything with electricity, you want to use a copper wire. It's the best conductor of electricity that we have. And the wire is connected to the energy source and a device that uses and transforms electrical energy. I know. Now you're ready for the chant. Looking at this simple electric motor, just take a look at it for a moment and then we'll chant. Now this chant was made because I love Mrs. Leslie. She is my best friend, and years ago when I first met her, I loved how she always said, "Oh my word." And so I decided to make this chant basically in dedication to my friend Mrs. Leslie. Here it goes. Oh my word. Electric motor, haven't you heard? Oh my word. Electric motor, haven't you heard? E to the M, E to the M, E to the M. Yeah, that's right, my friend. E to the M, E to the M, E to the M. Yeah, that's right, my friend. Electrical mechanical, electrical mechanical, electrical mechanical. Let's say it again. Oh my word. Electric motor, haven't you heard? Oh my word. Electric motor, haven't you heard? E to the M, E to the M, E to the M. Yeah, that's right, my friend. E to the M, E to the M, E to the M. Yeah, that's right, my friend. Electrical mechanical, electrical mechanical, electrical mechanical. Let's say it again. Now, everybody at this point should be able to say this. So you sing along. Teachers, make sure that they're chanting. If you chant this, it's going to help you pass so many questions on our quizzes, on our test, and on the PASS test, and especially the benchmark and the PASS test. 1, 2, 3, go. Oh my word. Electric motor, haven't you heard? Oh my word. Electric motor, haven't you heard? E to the M, E to the M, E to the M. Yeah, that's right, my friend. E to the M, E to the M, E to the M. Yeah, that's right, my friend. Electrical, mechanical, electrical, mechanical, electrical, mechanical. Let's say it again. Oh my word. Electric motor. Haven't you heard? Oh my word. Electric motor. Haven't you heard? E to the M, E to the M, E to the M. Yeah, that's right, my friend. E to the M, E to the M, E to the M. Yeah, that's right, my friend. Electrical, mechanical, electrical, mechanical, electrical, mechanical. Let's say it again. Oh my word. Now, don't forget that you're thinking electric motor. Electric starts with an E, motor starts with an M. E to the M means an electrical. Electrical is transforming into mechanical. And that's how we do the electric motor chant. So now, there the two chants are electric motor and the generators generate electricity. For who? For me. So just look at this. Generators are making electricity, changing mechanical energy into electrical energy. But can you see how they're exactly flipped? Here, mechanical is first, but with an electric motor, it's mechanical is last. Down here, electrical is last, but up here with an electric motor, electrical is first. So that's why we call them opposites. Remember in photosynthesis and respiration how they were chemical opposites? Well, with an electric motor and a generator, they are energy opposites. They are the exact opposite when it comes to the energy transformation. Now we're going to talk about what makes a complete circuit. All of these components must be connected in a complete, unbroken path in order for energy transformations to occur. This is what an electric circuit looks like. There has to be a battery source. So there has to be a battery. There has to be a wire, a copper wire, to make the circuit complete. You need to have a light bulb or a resistor. I mean, in this instance, a resistor in this instance is a light bulb, but it could be anything you plug in, an MP3 player, a calculator, it could be a computer, if you're plugging in a phone to charge, it could be just anything that you plug in. So in order to have a complete circuit, then you also have to have a switch. This is the switch on this one. So you need a switch, a resistor, a copper wire, and a voltage source. In this instance, it's a battery. If we were just plugging it into the wall, then the voltage source would be the electric company. So the electric energy in circuits can come from the following sources. If the source is a battery, the energy comes from stored chemical energy. If the source is a solar cell, the energy comes from the sun. If it is an electrical outlet, the energy can come from one of three places: either chemical energy from burning coal, nuclear energy from splitting an atom, or by fusing atoms, so it's called nuclear fission or nuclear fusion. Fission is when you split an atom to release energy, and fusion is whenever you add an atom, you kind of combine them, you force them together, which creates energy. And then there's geothermal energy. Geothermal means inside the earth. Geo is earth, and thermal is heat, so energy from inside the earth. Electrical energy can be transformed to other forms of energy in a circuit. Devices used in an electrical circuit are on this side. The energy transformation that it goes through is on this side. So a light bulb, the energy transformation is chemical, a battery, to electrical, to light and heat. A buzzer, a radio, or a TV would be chemical from a battery to electrical to sound. If it was a TV that was plugged in, it would be electrical to sound. So if it doesn't need a battery, it would go immediately from electrical to sound. A toaster, a stove, or a heater would be electrical from an outlet to heat and light. A fan, a motor, a CD player, or a toy car might be examples of those, would be chemical inside the battery, transforming to electrical, transforming to mechanical. Remember, the arrow means transforms into. Generators, like a coal-burning power plant, go from chemical energy with the coal burning to heat and steam, the heat in the form of steam, and mechanical energy turning the turbine to electrical. The generator in a hydroelectric plant goes from mechanical energy, the water moving from the dam. It would take mechanical energy, the moving water from the dam, and convert that into mechanical energy, turning the turbine, and then to electrical energy. And the last one would be a generator in a nuclear power plant, would be changing heat from steam, and then it would be converting into mechanical energy, turning the turbine, and then changing into electrical energy. I want to focus just on these three right here for a moment. Generators in a coal-burning power plant, generators in a hydroelectric plant, or generators in a nuclear power plant. Remember, generators are generating electricity. For who? For me. So they're all going from mechanical to electrical, mechanical to electrical, mechanical to electrical, for me, me, me. It just depends on how they're getting that mechanical to electrical. Mechanical turning the turbine, changing into electrical. Mechanical turning the turbine, changing into electrical. Mechanical turning a turbine, changing into electrical. But how does it happen? In a nuclear power plant, it's heat from steam turning the turbine, changing into electrical. In a hydroelectric plant, it's the moving water from the dam turning the turbine, changing to electrical. In a coal-burning power plant, it is burning coal to get the heat and steam to turn the turbine to change into electrical. And we're going to look at a little bit more examples of that. All right, so in your little booklet, turn to where it says coal-burning power plant. And I just want you to look at the picture for a moment before we fill in what you see on the screen, where it says chemical to heat to kinetic to electrical. Look up here and let's talk about how. So, it is chemical because we're burning coal and that produces heat. So, chemical is the burning of the coal. Anytime you burn, that's automatically called chemical because chemicals are released in the burning of it. So, chemical reaction in the burning of the coal. And then it produces heat. So the heat then makes hot steam because they pipe water. See how that says water's heated to produce hot steam. So the water goes in and it gets into the pipe, and then the water turns to steam. The steam then pushes out, starts swirling around the turbine, and then the turbine turns, producing the electricity. So I always tell my students to take their hand and pretend like it is the turbine. But they have to imagine what's turning the turbine. So in a coal-burning power plant, take one hand and pretend you just grabbed a whole handful of coal. Now throw it into the fire and then start to pretend like your hand is going up and down and up and down, and pretend that that's steam. Now take the steam and start to swirl your hand around like you're cranking a turbine. And then that turbine is cranking so fast that it is producing energy. So I want you to put your hands together and spiral them out as if you're making the sun shine. So it is grabbing a chunk of coal, throw it in the fire. The fire then heats up the water, move your hand faster, faster, it's heating up the water, it's turning to steam. Now the steam starts turning and spinning the turbine, so spin your turbine. So the steam turns the turbine, and then it generates electricity. So you put your hands together and you just push them out like you're making the sun. So each place that we do this in, whether it be a coal-burning power plant, a nuclear power plant, or a geothermal power plant, it's all going to be done the same way. Everything's going to be turning a turbine that generates electricity. So let's look at the chemical reaction below. So you should write the transformation. Chemical transforms to heat, transforms to kinetic energy turning the turbine, which turns to electrical. So remember, it's mechanical to electrical, me. Mechanical energy is, the kinetic energy is mechanical energy. So this is mechanical kinetic changing to electrical. If you want to write mechanical kinetic here, that might help you. Now the next one is a hydroelectric plant, and it should look very similar to you. Basically, if you look, here's the turbine, here's the generator, and they're generating electricity. But how does this one happen? Well, here's the water behind the dam. The water, being high like this, has gravitational potential energy. Remember, anything that's up really high has gravitational potential energy. Something that's lower has less gravitational potential energy. So this water being up high has gravitational potential energy. It's pushed and sucked down through the intake, and the water now spins the turbine, which turns the generator. It spins the turbine, turning inside the generator, generating electricity. So I want you to take your hand and pretend that you're water. The rushing down water, rush it down. Now spin your turbine and generate electricity. Put the sun, do like a sunburst out. So it is potential energy changing to mechanical kinetic in the water, turning the mechanical kinetic turbine, creating electrical energy. So it's potential to kinetic in the water, to kinetic in the turbine, changing to electrical energy. So potential to mechanical kinetic in the water, to mechanical kinetic in the turbine, changing to electrical. Now the next one is a nuclear power plant. Now nuclear sounds confusing. All you have to remember is either they're splitting atoms or they're fusing them together. They're doing one of the two. Now, it's dangerous. Nuclear power plants can create a lot of energy in a really short period of time. So basically, if you look here, here's the nuclear reactor, and this is where all the magic's happening. All you have to know is either atoms are being fused together or atoms are being split. Fusing them together is called fusion. Splitting them apart is called fission. Fission apart, fusion together. You really don't have to even know that. I just wanted you to know it just in case you ever wanted to surprise your mother. So, either fission or fusion. Basically, something's happening with an atom that's releasing energy. That energy then is coming through and heating the water inside the generator. This is called a steam generator. Really, all it is just water that's coming in. It's creating steam. And now let's pretend we're the steam. And the steam is turning the turbine. Everybody turn your turbine. Turn it fast. And then generate electricity. So you turn the turbine, generating electricity. And now this water gets so hot that it actually has to go through a condenser. That's what these cooling towers look like. Up north where I live, there's a lot of nuclear power plants. It's just so common. The one that's closest to my house is called Shippingport, and I used to work there. I did it in the summer for extra money, but I was a secretary, so I didn't have a really hard job. So describe the energy transformation in a nuclear power plant. Nuclear energy is transformed or converted into heat or steam. Thermal energy, heat, thermal. Remember, heat is called thermal, so heat is thermal energy, changing it to steam, and then mechanical kinetic in the turbine, and then to electrical. So remember, mechanical to electrical, mechanical to electrical, mechanical to electrical, me. Generators generate electricity. For who? For me. Right here. Mechanical in the turbine turning to electrical when the generator makes the electricity. And that's a nuclear power plant.